Hello all, and welcome to your last lecture for this Anatomy and Physiology 2 lab course. Yes, this is the last time you're going to have to hear me speak. Excuse me. This lecture is going to be covering acid-base balance, and hopefully a lot of it is going to be review, as we've talked about a good chunk of this material at different points throughout the semester. In this lecture, I'm going to hopefully fill in any little holes that you might have in your understanding, and also try to connect it all together as we talk about the importance of acid-base balance to your body physiologically. So let's first start by getting a review of why we care about this. Now, acid-base balance comes from or relates to a number of hydrogen ions in your body. As you may recall from general biology or earlier discussions in this course, acids typically create hydrogen ions and increase the concentration of hydrogen ions in our body fluids, whereas bases or alkaline substances will typically remove hydrogen ions from solution. Now, why do we care, might you ask? Well, hydrogen ions in our body are extremely reactive. That reactivity relates back to the number of these lovely positive ions that we have floating around in our body fluids. Now what happens is this lovely positive does not like to be alone. It likes to have a negative to play with. Unfortunately, if we don't have enough negatives for it to play with, it's going to go and break up your molecules to try and find a negative to play with. And of course, once we break up those molecules or change the shape of those molecules or begin interacting with those molecules, they tend not to do what they're supposed to anymore. This is particularly evident when we talk about proteins and enzymes. These guys have a very specific functional range in terms of their pH, and if we get outside that range, these enzymes and proteins begin to stop functioning properly. One of the first things they do is they begin to do what's called denature, which is unfold. Denature and unfolding is very detrimental because if a protein is unfolded, it can no longer function normally. So this is just one reason, one very important reason why this is important to understand. Now you might ask yourself, okay, well I understand why hydrogen ions are important, but why does it matter if I don't have enough, okay, in the terms of maybe if you are an alkaline or basic? Well, then it becomes the problem of, okay, well, you don't have enough hydrogen ions. What that leaves is a bunch of unattended negative ions, typically in the form of OH negative ions or hydroxide ions. Okay, these hydroxide ions are just as dangerous. OH ions, again, have this lovely negative charge that does not like to be alone. So for those same reasons, this negative ion is going to go and try and break up molecules and find somebody to play with. Again, destroying or inhibiting the function of those molecules in their original state. So in both cases, this is not a good idea. Now, in our body, we like to keep our pH range between 7.35 and 7.45. So that's a very narrow range, averaging about 7.4. Anything outside that range, and we're in big trouble. Now, not only is this range narrow in terms of our homeostatic range, it's also extremely narrow in terms of our health, in terms of when we begin to actually reach the extreme and death is imminent. And what we see is a 0.6 degree shift, anywhere from 6.8 to 8. If we are outside this range, we're dead. So we do not have a lot of leeway. We don't have a lot of room when it comes to pH imbalances. Now, again, you've probably asked yourself, well, I don't hear a lot of acid-base disturbances. I don't hear people coming into the hospital with, acidosis this and alkalosis that. Well, that's because acidosis and alkalosis are rarely the primary cause. Typically, there is something else going on that's causing the primary problem, but this primary problem is exacerbated or made worse by an acid-base imbalance of some kind. So it becomes very important clinically, as many diseases and disorders can throw a patient into acid-base imbalance and complicate their situation. So let's again review what pH is. Now, for those chemistry majors out there, for those of you who have had a little bit more chemistry in your background, you'll know that the pH is a measure of the negative log base 10 of hydrogen ion concentration. Now, for those of you, this might seem a little bit confusing, but it's really not. The only thing we're doing here with this big, long, crazy definition is basically with negative log base 10, we're taking a big number, or excuse me, a really, really big number and making it small. And with the negative log, we're creating an inverse situation. Now, I like to simplify things, and for those of you who maybe cringe a little bit when we start to maybe oversimplify, please kind of bear with me here. But a simpler definition for pH is simply the inverse measure of free hydrogen ion concentration. Now, there's a couple important points in this definition. First, pH is an inverse relationship, which means if hydrogen ion concentration goes up, pH will go down. Again, they go in opposite directions. The other key is that these hydrogen ions have to be free. Free hydrogen ions means they're unattended, and in actuality, if it's got this plus sign, by definition, it's free, because if it was attached to something, it wouldn't have that positive charge associated with it. The idea here is if we're talking about a molecule, say glucose, which is C6H12O6, right? Carbons, hydrogens, and oxygens. Well, you might think, well, darn, this guy has 12 hydrogens. He must be super acidic. But he's not, because all 12 of those hydrogens are bound to carbons, so that this guy has no, or is producing no, free hydrogens. Okay? So both of those are key in this definition. Well, let's make sure we understand how this relates to a solution being acidic or basic. And what we see is when we have an increase in the hydrogen ion concentration, we see that there is a decrease in pH. This means that a solution is acidic. So compounds that are acidic like to give off forgive my writing here, I'm learning to use a new pen device, okay? But solutions that are acidic like to give off hydrogen ions. Okay, so they increase the number of hydrogen ions in solution. Some common acids you may have dealt with regularly include vinegar. Vinegar is a a relatively strong acid, actually, and so your gastric pH typically very, very strong, 1.5 to 2.0. Now, on the other hand, substances that reduce the number of hydrogen ions in solution tend to increase pH, and these are said to be basic solutions or alkaline solutions. Now, alkaline substances or basic substances tend to pick up hydrogen ions. Again, pick up hydrogen ions. Now, they reduce the number of hydrogen ions in solution. One of the more common bases that you guys have all worked with and maybe didn't even know it was a base is bleach. Bleach has a pH of 12.5. Now, anybody ever actually spilled bleach on their hands accidentally? Think about what happened when you did that. Well, you may have noticed that your fingers kind of got slippery or slimy. Well, was the bleach oily? No, bleach looks just like water, so it's a normal substance. But you might, so then where did that oily, slippery substance on your fingers come from? Well, I hate to tell you, it being a bleach, the bleach was actually breaking down your skin cells, and that's where that oily feeling was coming from. That's why if bleach stays on your skin for too long a period of time, it can actually cause chemical burns. Another base many of us are familiar with is sodium bicarbonate, NaHCO3. Okay, sodium bicarbonate, of course, being a common additive when you have an upset stomach. Well, let's continue with this discussion of acids and bases by talking a little bit more chemistry. I know, many of you are probably sick of talking chemistry, but it does require a little bit of knowledge here. And talking first about the relationship between a strong acid and versus a weak acid. And this relationship is the same whether we're talking strong acid or strong base versus weak acid, weak base. Okay. Now, a strong acid is a solution, again, that gives off hydrogen ions, but it gives off all of its hydrogen ions. What we're going to see in a strong acid, a great example is, oh, I did not mean to do that. A great example is, there we go, hydrochloric acid. When hydrochloric acid is put into solution, every single one of these molecules breaks up. Every single hydrogen dissociates from every single chloride ion. So that means whenever you add hydrochloric acid to a solution, you are adding lots and lots of hydrogen ions. This is why hydrochloric acid has such a very low pH. Okay? Now, weak acids, on the other hand, they don't give off all of their hydrogen ions. They only partially break up, or what's referred to as partially dissociate. Okay? So we're going to see some of the molecules staying all bound up like this, and some of them breaking off and giving off a hydrogen ion and its other components, whichever that may be. In this case, we're looking at the weak acid carbonic acid. So what we're going to see is some of the molecules dissociate into, some of the molecules stay all bound up together, whereas some of them break off the hydrogen and the bicarbonate here, HCO3-. Now, this becomes important because what this reaction will do is it will fluctuate either in this direction or this direction depending on the concentrations of our solutes. Now, if we have tons of this side of the reaction, this equation is going to go this way. Okay, so if we have tons of carbonic acid, then more and more of that is going to break off into hydrogen ions and bicarbonates. If, on the other hand, we have tons of this side of the reaction, what we're going to see is we're going to encourage the reaction to go this way, bind all of these hydrogens up to create carbonic acid. Now, this versatility in pushing the reaction in either direction becomes very useful to us, because what we can do is manipulate weak acids into becoming buffers. So this brings us to our next discussion of buffer systems. Buffer systems are incredibly vital in conserving our bodies, or let me rephrase that, maintaining our body's pH balance. Buffer systems ensure that additions of acids or bases to a solution only cause minute or minimal changes. Okay, so I like to think of buffers as a compound that minimizes pH changes. Okay, so again, a buffer is a compound that minimizes pH changes. Now, in our body, buffers become extremely important because buffers can very quickly hide away a hydrogen ion or give off a hydrogen ion if we're having pH troubles. The problem is buffers are only temporary. They haven't actually fixed our problem. They've just hid it away temporarily. It's kind of like when your mom asked you to clean your room and you just shoved everything under the bed, right? You didn't actually clean anything, you just hid it away so your mom couldn't see it. Now, the question is, how do buffer systems work? Well, buffer systems can do one of two things, okay? First of all, they can bind excess hydrogen ions. Because remember, a hydrogen ion only hurts us if it is free. So if we can hide that hydrogen ion away, bind it to something, and it's no longer free, well then we don't care about it. On the other hand, if we are alkaline or basic, what our buffer can do is release hydrogen ions. These hydrogen ions are temporarily released into the solution, resulting in the creation of hydrogen ions and hopefully bringing our pH down. Okay? Again, the issue here is that these are temporary and they are also limited. We only have so many hydrogens we only have so many spots to stick those hydrogens in our buffer, and we only have so many hydrogens that we can break off. So eventually we're going to run out of hydrogen ions, we're going to run out of places to put those hydrogen ions, and then we're going to be in trouble. Okay? Which is why our body also has two additional systems set up to convert these temporary changes made by buffers into permanent fixes. Before we do that, though, let's talk about our most common buffer system in our body, and that is the carbonic acid bicarbonate buffer system. Now in reality, the carbonic acid bicarbonate buffer system is just this side of the equation here, just this reaction. Now this buffer is the primary buffer used in our blood plasma and our interstitial fluids. The carbonic acid bicarbonate buffer system relates or involves the shifting of the shifting, between the hydrogen state where it's bound in the form of carbonic acid here, and the unbound state over here where we have bicarbonate and hydrogen ions. Now we're again going to shift between these two states depending on our body's concentration. Okay, our concentration of carbonic acid and our concentration of hydrogen ions and bicarbonate. Now remember what I said about buffers. They have the ability to do two things. They have the ability to pick up hydrogen ions, and they have the ability to release hydrogen ions. This buffer is no different. Okay, this buffer here is no different. What we're going to see is if we are acidic, okay, we want to be able to pick up those hydrogens and hide it away. And bicarbonate does that job for me here. Okay, so the bicarbonate ion here can pick up this hydrogen ion and hide it away, bound in the form of carbonic acid. Again, remember, if that hydrogen ion is bound, it can't hurt us. We no longer care about it. Okay. On the flip side, if we are basic, okay, then carbonic acid here can break up into bicarbonate and a hydrogen ion. And by donating this hydrogen ion to the solution, we're counteracting some of the bases, some of the basic compounds, and we are decreasing the pH. Now remember, this reaction is only temporary. We only have so many carbonic acid molecules that we can break up and give off the hydrogen, and we only have so many bicarbonate molecules that can pick up the hydrogen to make carbonic acid. So this becomes a problem. Not only that, this reaction cannot help us if the respiratory system is the problem. Okay? If the respiratory system is broken, then we have an issue, because remember, the respiratory system makes carbonic acid from CO2 and water. So if our respiratory system is not functioning properly, then we have issues. Okay? But for the most part, this is a very robust buffer system. Okay, and we're going to take another look at this as we relate the functioning of this buffer system to a way of actually solving our problem, since this is only temporary. Well, again, buffer systems are temporary. We need mechanisms to permanently deal with these extra hydrogen ions, or these or the hydrogen ions that are or to create additional hydrogen ions, excuse me. So we do have two mechanisms already established that can do this, and guess what? This is going to be reviewed because we've already talked about them. Now let's see if you guys can remember the two mechanisms that we use to regulate acid-base imbalances. Well, hopefully you're thinking respiratory. Okay, because the respiratory system regulates the amount of the acid-base balance by regulating the amount of CO2 in our body. And hopefully you recall from last week that urinary also regulates acid-base balance, because in the kidneys we can get rid of extra hydrogen ions or keep our hydrogen ions. So let's continue with the respiratory system. Now the respiratory system, remember, comes back to our carbonic acid bicarbonate buffer mechanism. Okay? Remember, this half here, is going to be our buffer. But remember, the problem with our buffer is what happens when we are making too much of this, if we are hiding those hydrogens away, or what happens if we're running out of this, if we keep breaking it off to neutralize an alkaline solution. Okay? Oh, you know what? I'm sorry. The reaction reversed on me. Before, the hydrogen ion and Carbonic acid was over here. Well, now it's over here. Let me rephrase that. This part is our buffer. I apologize. So again, let me rephrase that. What happens when we start running out of our carbonic acid, when we keep breaking it off to neutralize an alkaline solution? And what happens when we start making too much carbonic acid? Okay, which would be the solution, which would be the case if we are trying to neutralize an acidic solution. Well, the great thing about it is we can regulate the amount of carbonic acid in solution by simply regulating the amount of CO2 in solution. Because remember from respiratory, we can create carbonic acid by reacting CO2 and water. So what we now have the ability to do is to take this temporary shift that's our buffer system and make it permanent by adjusting CO2 levels. Okay, so again, we can take the temporary change associated with the buffer over here and make it permanent by either getting rid of CO2 or keeping our CO2. Well, let's figure out what might happen under different situations. Okay, for example, let's say that we have too many hydrogen ions. What do we want to do? Well, we need to get rid of those hydrogen ions. Well, we temporarily get rid of them by binding them up in carbonic acid, but then what happens once our carbonic acid levels get high? If we're not careful and our carbonic acid levels get high, it's just going to want to break right back off again, which we don't want. So what we need to do is take that carbonic acid and convert it back into carbon dioxide and water. But again, now we have to worry about our extra carbon dioxide. Okay, so what do? Well, we hyperventilate. By hyperventilating, we get rid of our extra carbon dioxide. Okay, we get rid of our extra carbon dioxide, which again gets rid of our extra carbon dioxide, which through exhalation drives the reaction in that direction, okay, which causes our hydrogen ions to disappear. Basically, we're blowing off our acid in the form of carbon dioxide and our pH to increase. So again, remember, the carbon dioxide system can turn, or the respiratory system can turn this temporary buffer reaction here into a permanent change by regulating the amount of CO2. So let's take a look at it in this mechanism here. Again, this is a simple flow chart. Follow the arrows. So let's say that we are, for whatever reason, we have extra CO2. Okay, this causes there to be extra hydrogen ions in our body fluids. This is first noticed in the brain. So again, the central chemoreceptors in the brain are the most sensitive to changes in hydrogen ions, and they are the first to react. Well, in response to this increase in hydrogen ions, they stimulate the medullary rhythmicity center to increase our ventilation, or hyperventilate. In response to hyperventilation, we're blowing off all of our extra CO2, which is taking our hydrogen ions with it. The question is, what would happen if we hypoventilated? Now I want you guys to take a second and maybe try to create a flowchart like this, or maybe create a reaction like we had on the previous page, and see if you can figure it out. So again, pause this recording right here and try to solve that problem on what would happen to our pH. Not just whether it would go up or down, but create the little diagram, create the flow, and see if you can come up with that answer. Now remember, pause the diagram pause the integrity lecture if you're still working on it, because I'm about to go to our next slide. And here we go again. With hypoventilation, we're going to see that we would be lowering our breathing rate. By lowering or decreasing our breathing rate, we're not going to be getting rid of our CO2, or we will be keeping our CO2, which means our CO2 levels are going to go up. Now, I like to one of the ways I like to think about this reaction in terms of figuring out which way it's going to shift is by thinking about it as a teeter-totter. Well, if this side is going up, that means the rest of the reaction is going to shift this way. Okay, which means we're going to be creating more carbonic acid, and with more carbonic acid we're going to create more hydrogen ions. The additional hydrogen ions will cause our pH to decrease. Now here's the problem with the respiratory system. Okay, the respiratory system can both help, but it can also hurt. And what I like to do is think about our two situations. Okay, option 1 is if we are acidic, let's say 7.2, and we want to get to neutral, which is 7.4. Yes, that's a 4, sort of. Sorry. Like I said, I'm trying to make my my pen work. It's not quite cooperating with me. Well, in this situation, if we want to go from an acidic or from acidic state to a neutral state, do we want to keep our CO2 or get rid of our CO2? Well, if we are acidic, we definitely don't want to keep it because CO2 in our body is an acid. So we want to get rid of it. Well, in this case, we want to get rid of it by hyperventilating. I'm abbreviating here so I don't have to write as much. Hyper-V is hyperventilating. Hyperventilation will actually get us to a neutral state. In this case, this is good. Well, what if we are neutral and Mr. Lozier surprises you with a pop quiz? Well, then what are you going to do? Well, if you hyperventilate from a neutral state, you're actually going to be getting rid of CO2 that you actually need. So instead of it helping, hyperventilation actually becomes bad. Because what ends up happening is you get rid of carbon dioxide that you actually need. So you get rid of what I like to call good acid, excuse me, and your body becomes alkaline. Okay? Vice versa, let's go ahead and say that you are starting out at a pH of 7.6. In this case, you need to get back to neutral. So you're alkaline, but you need to get back to neutral. In this case, again, do you want to keep your hydrogen ions or get rid of your hydrogen ions? Well, do you want to keep your carbon dioxide or get rid of your carbon dioxide? I'm sorry. Well, if you think about it, if we are alkaline, do we want to keep our CO2 or get rid of it? Well, CO2 is an acid, so what we want to do is keep our CO2, because by keeping our CO2 we keep our acid and we can try and neutralize some of this alkaline pH. We of course keep our CO2 by hypoventilating. Okay, in this case, hypoventilation is again good. But let's say for whatever reason we start out at a neutral pace, and due to a head injury, you're forced, your respiratory center is depressed and you're hypoventilating, but you're hypoventilating from a normal state. Well, this hypoventilation is actually causing you to keep CO2 that you don't need, and that extra CO2 in our body is causing you to become acidic. So in this case, your hypoventilation is bad. So it all depends on where you start. It all depends on where you start. This is why we can't rely on the respiratory system alone to fix acid-base imbalances, because what if the respiratory system is broken and it's the one causing the problem? If it's the one causing the problem, we better have a backup. Okay, and can anybody remember what our backup is? Well, our backup is the renal system or urinary system. Remember from last week, we've talked about how the kidneys can help regulate acid-base balance. Okay, and the kidneys generally will do two things in order to help regulate our acid-base balance. They're going to secrete typically hydrogen ions and reabsorb bicarbonate. And what our kidneys will do is, in general, adjust those ratios depending on your body's metabolic or your body's acid-base balance. Now, this secretion and reabsorption processes are going to occur in two regions of the nephron. They occur in the proximal tubule and in the distal convoluted, or excuse me, in the collecting ducts, in particular the intercalated cells of the collecting ducts. Now, what we're going to see is in the proximal tubule, your proximal cells have the ability to secrete hydrogen ions. Oh, sorry about that pop-up. We can get rid of that. Excrete hydrogen ions and at the same time reabsorb bicarbonate. Okay? The collecting ducts also have the ability to do this, again secreting hydrogen ions and reabsorbing bicarbonate, but your collecting ducts can also switch to reabsorbing hydrogen ions and excreting bicarbonate if your pH is extremely alkaline. Now, that is a very extreme circumstances. Typically, what your body will do is either increase or decrease the activities of these two things. So let's take a look at what your kidneys will do under the two different situations. So again, your kidneys will do two things. Okay, if you are an acid, man, let me try writing that one again. Again, if you are currently acidic, bear with me. Your kidneys, again, have two options. Remember, they are normally excreting hydrogen ions, and again, they are normally reabsorbing bicarbonate. So remember, your kidneys are always doing this. The question is, under an acidic situation, should our kidneys be doing more of this or less of this? So under an acidic situation, do you want our kidneys to excrete more hydrogen ions or less hydrogen ions? Well, since acidic situations have too many, hopefully you're saying we want to increase the excretion of hydrogen ions. Now let's think about bicarbonate. Does bicarbonate help us or hurt us if we are acidic? Well, remember, bicarbonate can act as a buffer and pick up excess hydrogen ions. So hopefully you're thinking that the more bicarbonate the better if we're acidic, so let's reabsorb more. So if you are acidic, you will actually increase the excretion of hydrogen ions and increase the reabsorption of bicarbonate. Now let's figure out what your kidneys will do if we are alkaline. Okay, I'm slowly getting the handle of this pen. Okay. Now again, your kidneys are still going to do the same thing. They are going to excrete hydrogen ions and they are going to reabsorb bicarbonate. The question is, again, under alkaline circumstances, are we going to increase the amount of hydrogen ion excretion or decrease the amount of hydrogen ion excretion? Well, remember, alkaline or basic situations have a low hydrogen ion concentration. So do we want to keep getting rid of hydrogen ions if we don't have enough as it is? No, we don't. So under alkaline situations, your kidneys are going to shut down or decrease the excretion of hydrogen ions. How about bicarbonate? Well, remember, bicarb accepts hydrogen ions. So if bicarbonate takes hydrogen ions out of solution, well, we don't have enough hydrogen ions as it is. We don't want to hide them away, so we would want to decrease the reabsorption of bicarbonate. The problem is we can only decrease so much. If we decrease the excretion to 0 and we're still alkaline, we got a problem because we can't decrease it beyond 0. So what do we do if we are extremely alkaline? Or extremely basic? What do we do? Well, here's where the intercalated cells and the collecting ducts come into play. These unique cells can actually switch things up a bit. They will also decrease the excretion of hydrogen ions and decrease the reabsorption of bicarbonate. But if you are extremely alkaline, the collecting duct cells can actually switch things around. Okay? The collecting duct cells can actually begin to reabsorb your hydrogen ions, and they can begin to excrete your bicarbonate. Now this begins to help us if we are extremely alkaline to the point where we've stopped excreting it and we still don't have enough hydrogen ions. Well, we better start reabsorbing it to try and fix it. Okay, but that typically only occurs if we are extremely alkaline or extremely basic. Remembering, alkaline and basic mean the same thing. Okay. Well, finishing up our little lecture here, again, remember, your goal, physiologically is to keep your pH around 7.4, no lower than 7.35 and no higher than 7.45. But of course, that's not always possible. So we got to look at what's going to happen if we start to get too low and what's going to happen if we start to get too high. Well, if we start to get too low, you begin to suffer from what's referred to as acidosis. And the symptoms present themselves, with depression of the central nervous system. So your reflexes begin to diminish. You don't tend to respond as quickly as you used to. If it gets too acidic, getting close to 7.0, you typically begin to enter into a coma. And finally, at 6.8 and below, death is imminent if something isn't done immediately. On the opposite side of that, if you are alkaline, your pH is typically above 7.5, and in this case it's the opposite that occurs. In this case you get overexcitation of the central nervous system. You get twitches, nervousness, pins and needle sensations and things of that nature. If it gets too high, close to 7.8, we end up seeing muscle spasms and convulsions taking place. And anything above 8, we typically see death due to respiratory failure as your diaphragm is no longer functioning due to the overexcitation associated with alkalosis. But the question becomes, what causes these two things? Now, when it comes to acid-base imbalances, again, remember, acidosis is anything below 7.35, and alkalosis is anything above 7.45. Now, the question is, what causes it? Well, looking down here, you can see the summary of causes. The summary of causes comes back to the different systems that might be involved. Now remember, we spent quite a bit of time talking about the respiratory system and how it can help, but it can also hurt. Well, if the respiratory system is what's broken and ultimately causing our acid-base imbalance, we refer to that as respiratory acidosis and respiratory alkalosis. In this case, since the respiratory system is broken, it's imbalances in CO2 that cause our problem. So if you are looking to diagnose an acid-base imbalance and you're trying to figure out if it's caused by CO2, well, you're going to be looking for the levels of CO2 in our body and to see if they're normal. Okay. Excuse me. Vice versa, if the respiratory system is working just fine, well then there's got to be another underlying cause to your acid-base imbalance, and that typically is diagnosed as metabolic acidosis or metabolic alkalosis. Now in this case, your CO2 levels should be normal because the respiratory system is fine. What ends up causing the problem, or what ends up being out of order, are going to be your bicarbonate levels in the blood, because your bicarbonate levels are actually trying to fix the situation. So as your bicarbonate levels drop, they're saying, oh, I'm picking up hydrogen ions. I don't have enough bicarbonate. Bicarbonate is too low. Vice versa, if you have too much bicarbonate, that's typically a symbol of respiratory alkalosis, because you don't, and we see that happening here. Now, what we're going to be doing in class is you're going to be trying to diagnose different acid-base imbalances, which means there are 3 things you need to look at in order to figure out what type of acid-base imbalance a patient is suffering. Obviously, the first thing you need to look at is the pH. And in looking at the pH, you're going to say, okay, is it acidic or is it alkaline? Well, that tells you half the story. Well, then you need to figure out if the imbalance is due to the respiratory system or if it's something else and metabolic in nature, at which point you're going to look at the amount of CO2 in the blood, and you're going to look at the amount of bicarbonate in the blood, and you're going to try to match it all up to figure out which imbalance is causing the or which compound, whether it's bicarbonate or carbon dioxide, is causing the noticeable pH problem. Not only will you guys be diagnosing these acid-base imbalances, I'm also going to want you to tell me how your body is going to try to fix it, and that's referred to as compensation. Your body tries to compensate for acid-base imbalances, and it will either do this via the respiratory system or the kidneys, as we've been talking about it. Now, with respiratory compensation, of course, it can only be used if the respiratory system is not the cause. If the respiratory system is the cause, well, then the kidneys are the only ones that can fix it, or at least try to fix it. If, on the other hand, the problem is metabolic in nature, well, then not only can the respiratory system try to fix it, but so can the kidneys. And you'll see that again in your activities. Okay? I hope that helps and clears up a lot of the questions you might have. Again, if you have not done so yet, please go back and read this section in your textbook in Chapter 27 covering acid-base imbalances, and also listen to this integrity lecture as many times as you'd like. You can, of course, listen to this multiple times, but ultimately remember, you do have to take that pre-lab quiz via Blackboard before lab starts next week. So make sure you do that, because remember, those bonus points can be very useful to you as we near the end of this semester. Other than that, I hope you guys enjoyed your lecture here and understand it, or I've cleared up some holes for you. And email me if you have any questions. Otherwise, I will see you in lab. Have a great day.